The talk will be delivered by Professor Dipankar Home. Now, in Calcutta, when uh, a summer school is organized on fundamentals of quantum physics, there cannot be any other name that I can think of other than Professor Dipankar Home. I had the privilege to listen his lecture in 1990, that is 35 years ago, at this Indian Association for the Cultivation of Science. That is all this on the fundamentals of this quantum theory of measurements. So today he is going to talk on the similar kind of topic. Now, to introduce Professor Home very briefly, that although that most of the people who are associated, at least in the science, he is known, but he is a senior professor and senior scientist at this Bose Institute, Calcutta. And he's a theoretical physicist. Now, to say very briefly that his major interests is in the quantum theory of measurements, quantum non-locality, macroscopic limit of this validity of this quantum mechanics, quantum entanglement, quantum communications, quantum cryptography, and so on. Uh, Professor Home has been awarded with these numerous awards and this fellowship of this country. So he started in 1986 with this INSA medal scientist, 2011 fellow of this National Academy of the Sciences. In 2002, he is the JN Fellowship. 1995 is this associate memberships of this Institute of Theoretical Physics. He is the author of more than 100 scientific papers, and he also wrote 3 books. So with this very brief introduction, I invite Professor Home to deliver his lecture.
Okay, so let me begin by thanking the organizers for giving me this wonderful opportunity, and also it's, of course, a great honor. And I shall spend a few minutes extra to say a few words before I begin my actual talk. And I request you that we have 45 minutes, no? So at least 15 minutes before the ending, please alert me so that I can appropriately tune. But before I begin my actual talk, I'll just spend a few minutes giving some historical remarks in view of this occasion. And I must mention to those young present and here, so this is very commendable that SIDAC Patna and Bhaktivedanta have jointly organized this conference. This month is a very auspicious month for all of us who are doing research on quantum foundations. This month of June, because it was in the month of June 1925 that Werner Heisenberg had an allergic reaction and went to Heligoland for a vacation when he was working in University of Göttingen. And during that break in the month of June, the original idea of how quantum mechanics should be formulated, he hit upon that idea. That was a moment of revelation for him, and is beautifully described in his book, Physics and Beyond, autobiographical book, which I highly recommend any student of quantum physics or any researcher should read. And it is a literary piece as well. So there he devotes a separate chapter describing the moment of his spiritual and that insight he got, that is beautifully described there. And that was in the month of June. So it is very fitting that here in Calcutta we have this conference on 100 years of that event. And I may mention that the first in India, the research studies on this modern line of studies on quantum foundations, and I was fortunate enough to be associated with that from beginning of 80s. In fact, mine was the first dissertation work on this subject, and there were only 2 researchers in India at that time interested. So it was very difficult to get people interested in foundations of quantum mechanics, which was considered to be abstractly philosophical. And then in 1985, we remember, I could convince a few senior professors after completing my doctoral work, and we organized a conference in Shantiniketan on 60 years of quantum mechanics. So the first conference in India on foundations was organized in Shantiniketan, 1985, 60 years of quantum mechanics. So I am very emotionally pleased that that also this 100 years of quantum mechanics, some event is occurring in Calcutta, and this is the only event which I know of is occurring in Calcutta, and this 100 years of quantum mechanics conference. So I'm quite pleased to be part of it and giving the talk. Now, as you can see from the title of the talk, and so I will spend, let me first explain what I shall be talking about and what will be the structure of my talk. So I shall spend the major part of the talk explaining the motivation for studying quantumness of massive objects. Because you may be wondering, quantum mechanics is all about microphysical objects. So why one should be interested and why should worry about testing quantum mechanics for massive object? Why it is important to test quantum mechanics for massive? To understand the motivation is very important, especially in this line of studies, which is now gaining considerable momentum. Lot of experiments are being planned. And this is also a wonderful example of symbiosis between basic, not only basic science would be an understatement, symbiosis between abstract philosophical thoughts and hardcore technological applications and very sophisticated experiments. So this is a wonderful example of that symbiosis, that synergy, which we are hearing a lot, and the Nobel lecture and the Nobel Award a few years back, the citation mentioned about second quantum revolution originating from some of the studies which I will be mentioning today. So let me begin. So the major part will be devoted towards motivation and state of play. And I must mention that since Professor Leggett will be giving the talk on, he has already sent the title, and knowing Professor Leggett very well for the last many decades, I can guess what he will be talking about. So I shall make my talk, I shall give many remarks in this talk, which will serve as a prelude to Professor Leggett's talk, which we will elaborate upon, and I expect. So there will be many stimulating or provocative remarks, and I invite any one of you to talk with me, to discuss with me, to explain them further, because I won't have the time to go into them detail. But purposefully, I'll be slipping in those remarks and some provocative comments and ideas. Now first, I think it is important to understand what we would mean by something to be non-classical or quantum, or what would it mean to test a system to be intrinsically non-classical or quantum. Or for that, it is first important to understand what are the quintessential aspects of classicality. In fact, this whole enterprise on this modern line of studies on foundations of quantum mechanics, which may be said to have begun in 1964 with John Bell's seminal paper. The philosophy underlying this grand adventure, that I shall try to explain in a few of these slides, which will serve as a prologue to my talk. So a considerable part of that talk will be prologue and then the motivation. And then whatever time I may have, I will just briefly touch upon the other details, which you may discuss with him and know further. So these two, of course, one may, by no means this is unique, but realism and locality are the two most fundamental features of any classical worldview, one may say. Now, the whole concept of realism is very nuanced concept. And today evening, Professor Leggett will be talking much about it more. So here, for the purpose of my present talk, so I consider one may define realism in various ways, and there are a lot of debates about that. So here, the definition of realism that is taken to be are that all the properties of an object which can be measured. Here, the statement is written, can be assigned definite values independent of measurement. So let me elaborate a bit, because one cannot write everything there. So here one means more precisely all the properties of an object that can be measured, which have some physical relevance, that can be assigned definite values independent of those properties being measured or being measured along with other properties of the object being measured. That means when you are looking at some property of an object measuring, its other properties are also not affected, and that the other properties also exist independent of that particular property you are measuring. In other words, what it means is that that act of measurement has no fundamental role in this way of defining realism. The, and, the, and, the, and, the, and, the, and the independent existence of the object is assumed. So this is what underlines the notion of realism that underpins any classical theory. And of course, there is this concept of locality, which you know, which is no action at a distance, and considering spatially separated objects which may be correlated, the choice of measurement on one of them cannot affect. But here I shall make one interesting remark, which is often not recognized, noted, that when you say locality is an hallmark of classical theory, and a perceptive student may say, what happens to Newton's theory of gravity? It is essentially non-local. Oh, why does an apple fall? Because of a mysterious action at a distance pull from the earth. So the point is that Newtonian theory of gravity is not the correct classical theory of gravity. If you have the correct classical theory of gravity, which is Einstein's theory of gravity, that is essentially local and there is no action at a distance. I make this remark because recently Switzerland, Professor Nicolas Gissa, who is a very well-known quantum, he made a strong advocacy and they have adopted in their school teaching also that whenever one teaches Newtonian theory of gravity, should teach from then on that Newton himself did not like this and science progresses by more sophisticated. So that is one philosophy of teaching. So this is what I wanted to make a remark. Now, another important aspect of classical viewpoint, which is often not given due importance, which was not given due importance, and in recent times it is becoming important, is the notion of non-invasive measurability, that it is possible to measure properties of objects with arbitrarily small disturbance. This is assumed in any classical discussions, that whatever disturbance that may occur in measuring something, that disturbance is calculable or controllable. This is what is assumed. And in particular, that the act of performing measurement should not influence the statistics of outcomes of what you observe next. Now, whatever has happened over the last 60 years, I will make the recent Nobel lectures were given, and that Nobel citation talked about the second quantum revolution. One may say that that began with that John Bell seminal paper 64. So the line of studies from 1964, it is the central element has been, I would call these two strands. One strand is which has much developed over the last 60 years. That is the where you combine realism condition with the locality condition and try to look for its empirical testable implications. Now, this is a huge, what I'll take a pause here to emphasize the real importance of that, of this approach of study. Here, one is not interested in going into the details of a theory. One is taking some fundamental philosophical principle. When I talked about realism, one may say, okay, this is all philosophy, how you define realism, why one should worry about how one should define realism, and so on. What John Bell's seminal discovery showed, that abstract philosophical notion, if you combine with this locality condition, which is another fundamental notion, though justified by special theory of relativity, but in itself it is also a priori conceptual idea. So what the philosophy was that you take minimum of a priori assumptions about the nature of the physical world, minimum a priori assumptions about the natural physical world, and whether you can derive empirically testable conclusion from it. This was a huge paradigmatic shift in scientific methodology. That is no wonder why that Bell's discovery is called one of the most important discoveries ever made in science. One of the that the Time magazine called in 2000. Why it is so? Because this total change, that philosophy can be testable. And that gave rise to the term which Abner Shimony has called experimental metaphysics. And that has now led to quantum computers, quantum teleportation, all you talk about, the second quantum revolution. That has led, and so it is something unparalleled in science. I'm saying this to excite the young minds that what this adventure is somewhat not about just learning quantum computers or not just about quantum teleportation technology. These are new technological development. Now AI is coming. There will be other technology. It's not merely advent of a new technology. The way this technology arises is unique, and then it promises that in this way of study may reveal new vistas which we cannot even now imagine. And it is a very short time, but I shall just give you a flavor. So what Bell did, he combined it with the locality condition and derived some testable result, some testable relation which you can empirically observe. And their experimental violation would mean that this combination of these two assumptions must be wrong. So this has been one line of study which has been much explored, and this has led to those technological many applications, the idea of quantum entanglement and so on. I shall come to it. But there is also another line of study that had been initiated in 1985 by Leggett and Garg. That is not yet much known to that extent and not much explored, but over the last decade or so, it has started. And this is what will be the focus of my talk today. So Leggett, Anthony Leggett will be speaking today evening. He and his then postdoc student Anupam Garg, they had derived some empirically, I shall be showing those relations, and which may be called temporal version of Bell inequality. And the empirical violation, the predicted violation of this inequality, which is derived from the combination of realism and non-invasive measurability, implies that this empirical violation consistent with prediction of quantum mechanics would imply quantum violation of this combination of realism and a non-invasive measurability, which they called macro-realism. Now, this term macro-realism, it means that if we apply this notion for macroscopic systems, this notion of realism, and the notion of non-invasive measurability, the conjecture Leggett made was that it can then give rise to a possible way of testing macro-realism for macro systems. Because normally that was related to Einstein's famous question, is the moon there when nobody looks at it? That means that side of question implies the idea of realism, that its properties are well defined independent of whether I am. Now, the bold question that was asked, can such an what I may call an audaciously metaphysical assumption be empirically tested? Asking this question is a great, and it can be tested. That is the way it showed. So I shall come to that. Now, this quantum mechanical violation of Bell inequality, because that is so well known, I'm stressing analogy with it. It stems from quantum entanglement, you all know, most of you, and spatially separated correlated particles. But the quantum violation of Leggett-Garg inequality, which I shall be talking about, and its variance, stems from essentially applying the quantum superposition principle to the individual system, which is time evolving. This is a big difference this is a significant difference between these two lines of studies. Of course, quantum entanglement is an extension of the quantum superposition principle for a single system when applied to the composite system and considering what is technically called tensor product of Hilbert spaces if you define a composite system in that tensor product of Hilbert spaces, you get quantum entanglement by extending quantum superposition of states to that composite system state. But here we'll be focused with testing quantum superposition principle as applied to single particle and time evolving system. Because the violation of Legge-Guerc inequality, quantum violation, stems from this superposition principle. Like the Bell inequality violation stems from the feature of entanglement, quantum entanglement, which I am not going to discuss here. But now, what is quantum superposition principle? There are different ways of looking at it. Here I give my take, which is relevant to my talk. We'll be hearing Professor Haridas giving a comprehensive, in-depth talk on quantum superposition principle. So here I take it to mean it's a combination of superposition of states applying. Superposition of states comes from the completeness assumption, those technical aspects of quantum mechanics for the basis, plus the quantum measurement postulate. That is the important part of my talk. Now, superposition of states you have, and if you extend it for interaction of the system with the measuring apparatus. Now, here comes, I have to say, the first most basic feature of quantum mechanics which gave rise to controversies from the very birth of quantum mechanics, and it still persists, is that whenever you have to give meaning to quantum superposition principle, superposition of states, you have to assume something about the measurement outcomes. And you know, Bond's rule is used, the probability of obtaining an outcome, and quantum mechanics gives a rule for calculating. But then conceptually, the deeper question comes that when you talk about probability of an outcome, you assume at the outset the definiteness of an outcome. When you toss a coin, when you say the probability of falling is half, whether the coin is falling head or tail. But there you are assuming that in each run of the experiment, each spinning of that coin, the coin falls either head or tail. So there is one definite single outcome in any one run of the experiment. In different runs, you have different outcomes. Then only you can talk about the probabilities of different outcomes. This point, although may seem very fundamental, that is often missed, and that is why, and was missed in the initial years of quantum mechanics. That's a long story. I'm not going into that. So what I want to emphasize that, for example, stalwarts like Niels Bohr and others, they believe that, okay, quantum mechanics should not be extended to apply for measuring apparatus. That was one way. But then we all know that this quantum mechanics is now we regard as a totalitarian theory. So if it is applicable to microphysical objects, there is prima facie no reason why it should not be applicable to systems which function as apparatus, measuring arrangement. But this was the Copenhagen interpretation and in fact, the Bohr doctrine. And so that was very useful on those initial years of quantum mechanics. If that then started worrying about these problems, quantum mechanics would not, because all the things were done and a lot of interesting work. And also for historical completeness, I must mention, that's why I go back to that book, Physics and Beyond by Heisenberg, and there are many other accounts, lovely, that after June 1925, Heisenberg first got this idea, wrote the paper in July, and got it published. He went to Berlin to give a talk on this. Then in Berlin, after that first talk he gave on quantum mechanics, that the newly discovered was in Berlin. Einstein was there and invited him for a walk back to his home. And during the walk, Einstein had mentioned to him what we now regard as measurement problem. So the genesis of the measurement problem was the famous discussion between Einstein and Heisenberg. And Heisenberg cherished this discussion very much. It is there in his autobiography, Physics and Beyond, as a separate chapter, in his other writings everywhere. And it is also documented in books on foundations of quantum. My book has also a lot of this. So I'm just mentioning all this. There are many other things, but I don't have time. So this, once you recognize and admit that, okay, quantum mechanics should describe a measurement process, then detailed modeling of measurement has to be done. And it is interesting that the first detailed description of the measurement process was given by von Neumann in his famous book 1932, The Mathematical Foundations of Quantum Theory, a classic book, and his last chapter has quantum theory of measurement processes. So anyway, so whatever this, the main point is that the final wave function, you have this, oh, sorry. So so the final combined wave function that will emerge after interaction with apparatus will be of this form. So when you extrapolate the superposition principle to the apparatus level, it will be of this form. And this phi 1 and phi 2 are the states of the apparatus which are macroscopically distinguishable. Now, this is the outcome of applying the quantum formalism to a measurement process, applying the unitary evolution throughout. But this description does not correspond to what is actually observed in any one run of the experiment. So, the occurrence of a single definite outcome in any single run of the experiment. So, this is a fact we know, we observe, but how this fact has to be justified by the quantum formalism, which leads to only equation of this form, which is still a superposition. And of course, you have the Born rule, probabilities of variance determined by the Born. I call it Born-Dirac rule because Born rule originally was for the position case, and Dirac in his famous book generalized that rule, which we use. Now, the point is that this probabilistic interpretation can only be justified if this occurrence of a definite outcome is ensured in the formalism. So, once I have conveyed this to you, then I can state what is the importance of testing quantum superposition of macroscopically distinct states of a massive system. The kind of states that occur in the description of measurement process is a superposition of states of a macroscopic apparatus. And these are the states which are known as Schrödinger's cat type states, like Schrödinger cat, alive or dead, basically means macroscopically distinct states of a macro object. Now, what is quantum superposition principle valid at that level? Because you see, to extrapolate description of quantum to measurement process, you need to assume the validity of this extrapolation at that level. Now, how can you experimentally test it? How can you, is it justified? This is one. Now, this testing is important for what I call experimentally oriented study of the quantum measurement problem. That means to resolve the quantum measurement problem over the last many years, many approaches have been proposed. But out of those approaches, some approaches try to preserve the superposition principle at the macro level and then change the interpretation, like the Bohmian approach, like the many worlds approach. But there are also other approach like the collapse, the spontaneous collapse models, the dynamic, the nonlinear, whether due to nonlinear term in the Schrödinger equation, which gets amplified at the macro level, whether collapse will occur when you go to the macro level. So on all those kinds of models, breakdown of quantum superposition principle at the macro level is predicted. So that's why it is important. Now they give the quantitative scales. So these are all the various collapse models. These are called dynamical collapse models, that you don't put wave function collapse by words. The first statement of collapse was given by Dirac in his famous book, that whenever you make a measurement, the system jumps from one of the here to the measured state. But this statement is a non-starter because first of all, it ignores the role of the apparatus. No, it ignores the interaction between the system and the apparatus. So then von Neumann framed the collapse postulate in the form that the joint system apparatus state becomes a from pure to mixed state. So this is one way of putting. Now, all these statements, now it becomes important that can we test up to what level quantum superposition principle is valid, up to what large mass it can be applied. Then we can test the predictions of those collapse models. Suppose this collapse model predicts that at the range of this sort of mass, only the collapse should become relevant. So those kind of objects can function as apparatus. So this is one useful importance why one should test quantum superposition of macroscopically distinct states of a massive system. The other is, of course, testing macrorealism versus quantum mechanics. Because as I said, the Leggett-Gark inequality is a consequence of macrorealism and which can be experimentally tested. So then testing macrorealism means testing macrorealism in a way consistent with quantum mechanics, means testing quantum mechanics in the macro domain. So this provides one route of testing quantum mechanics in the macro domain. But also Leggett-Gark inequality has other utility as a powerful test of quantumness of a single particle. That's why even for microsystems, it is now used to determine which components of a circuit or which are genuinely quantum or not. For genuine quantumness, this becomes important. And also, very recently, this line of study has become important for testing quantum nature of gravity, because recently, that I'll just indicate briefly. So this is the historical thing. And why I put Schrödinger here, because Schrödinger 35, 36 papers played a pivotal role not only in explaining the concept of entanglement. In fact, entanglement was most precisely defined only in those papers by Schrödinger. Introduced the idea of also Schrödinger gave the most precise formulation of the measurement problem, Schrödinger's cat and all those things. And inspired by really Schrödinger's papers and in fact, Leggett's pioneering paper in 84, 85. In fact, 84 Leggett paper is titled A Search for Schrödinger's Cat's Laboratory Cousin. In search of Schrödinger cat's laboratory cousin. Can we test Schrödinger cat at a laboratory scale? So this is I have already covered that quantum mechanics to describe any mesh, you need to apply quantum mechanics from massive. And the question, the whole measurement problem can be summarized this way, that can quantum mechanics explain in a consistent way while measuring through macro. And various approaches had been produced. So this is one importance of this line of study. I'm not elaborating further on the quantum measurement problem here. Just one remark, this is a pure state. Technically, this is called a pure state ensemble. How many? 50. Pure state, and this is a mixed state. So I'm not going. I've already mentioned this. And also that these are the two statements by two of the most distinguished physicists in our recent times, the acuteness of the measurement problem. And that's why this sort of tests become important. And also it is interesting that this whole enterprise, because Stephen Hawking during his debate with Penrose had remarked, reality is not a quality you can test with litmus paper. That is true. You cannot test realism alone. But what we have learned that by combining realism with other conditions, one can test. And that one can go on playing games in different ways. And in this context, the temporal version of Bell inequality is becoming increasingly important. I'm not going into further into this, how this study is going to be important for the quantum nature of gravity. There have been recent these two works. This latest work we were associated, but all these proposed new laboratory tests for quantumness of gravity involve superposition of massive objects, quantum superposition. So that's why it is prima facie important to test first the superposition of massive objects, whether it is valid, in order to set up these experimental schemes, which have now attracted a lot of attention to whether this, how can this sort of schemes can be implemented. But for this, the primary requirement is to setting up the quantum superposition of macroscopically distinct states of a massive objects to spatially separated states of massive objects, which are separated at a considerable distance. Again, I can elaborate on all these through my discussions, but here I don't have much time more. Now, macrorealism, I already have stated realism and non-invasive measurability, and I'm not going into them. Now, this idea of negative result measurement plays a crucial role in this study to ensure, basically the idea is to ensure that if you derive some consequence from the conjunction of these two assumptions, then you set up the experiment in any way so that classical disturbance produced by the measurement is either controllable or minimized, so that whatever result you get regarding the violation of that statistical result can be attributed to the violation of realism. This is basically the motivation, so that non-invasive measurability condition is ensured at the classical level in the experiment you set up, so that ultimately the result you get, the violation of Leggett-Gerke or its variant, various variants you get, can be attributed to realism. Now, Leggett-Gerke inequality was given 1985, then its other versions have subsequently appeared. And this is the version now quite used. It's called the no disturbance condition, no signaling. That means the measurement outcome statistics at any instant independent of whether any prior measurement. And this is really the central feature of non-classicality or quantumness, one may say, in terms of measurement, which does not go into any detailed aspects of kinematics or dynamics, whether the equation, Schrodinger equation is modified or not, whether there's some kinematic relations. But this fundamental feature is independent of whatever those details are. And the importance of this line of study is another, you get a statistical condition coming out from this basic condition. And that statistical condition, if it is experimentally violated, you may say this gives what is now called the term device independent way, theory independent way, certification of non-classicality. Because any theory which gives that violation has to be is non-classical by definition. We call classical theory by that definition. This generalized way of looking is becoming important because one has to, when one tests Bell inequality or Leggett-Gerke, one is testing not only, one is testing limitation on any theory of the world, really. Any theory of the physical world that may come has to violate Bell, has to violate Leggett. And if it satisfies Leggett or violate it, if you are experimentally able to test, you can rule out any theory. So that's why testing of generalizations of quantum theory or other modifications become important through this line of study. And of course, these are the various experiments that has been done. And at the level of mass so far, so let me summarize. While when the earlier all experiments, they deal with other kinds of objects and other kinds of macroscopicity parameter. But the usual macroscopicity parameter that we all would like to have is mass. However, the experiments on mass has so far tested up to 10 to the power 5, 4 or 10 to the power 5 atomic mass in it. So now the new scheme that we have proposed, how much time I have? 7. Oh, good. So now, this completes really the motivation part, and the state of play is, I had summarized earlier. For completeness, I must mention that among all the experiments performed here using Leggett-Gerke, you see, even for the atomic mass, some experiments, these have their own significance, not for testing macrorealism, but because for characterizing non-classicality in different contexts. This experiment is particularly interesting. This, we had earlier proposed this applying in our earlier work before 2016, applying Legge-Gark in the context of neutrino oscillations, which is a very fundamental phenomenon with two-state oscillations, Legge-Gark, as a certification of quantumness there, and also for the test of the quantum interference effects there. And this experiment is a spectacular experiment testing neutrino, Legge-Gark for neutrino oscillation, and the length scale involved there is 700 kilometer. So this is the longest length scale over which quantum superposition of states has been verified. So Legge-Gark serves as a tool there for that microsystem. Here, this experiment is using superconducting flux qubit with oppositely circulating superconducting currents, which are of the order of nanoampere currents with magnetic moments differing in order of 10 to the power 4, 5 Bohr magnetons. And this is the paper in which Leggett himself was also involved as a co-author. And this experiment closes that loop that satisfies non-invasive measurability in a rigorous way. So this experiment may have said to have all shown that realism cannot be applied at this sort of macroscopic level. From Bell inequality, you cannot comment definitively about realism per se, because it is always coupled with the locality condition and so on. So for fundamental implication of Bell inequality violation is non-locality, while fundamental implication of Legge-Gark is maybe called testing realism. So if both Legge-Gark and Bell violated, one may say both locality and realism are not. In fact, this is how the most recent paper on this issue ends. And this is what we have come after 100 years of quantum mechanics, one may say. But anyway, but what I'm saying, we also in India, we did this, I was involved in this experimental work with the lab at RRI of Professor Urbushi Sinha. And there, this experimental setup showing Legge-Gark application has found application in random number generation. So this is an example. So far, what I have been talking, many of you may say, all this is philosophical mumbo jumbo. Why I should worry about all these points? Now these applications are opening up, and there are other applications in the pipeline. I'm not talking about them, but this is not the paper. This is the paper where this experiment is reported. The following paper came out last year in Physical Review Letters, where the experiment was also done in that lab. This is the first random number generator using a single system, what they call technically some semi-device independent random number generation, and first application of Legge-Gark in that direction. And this has opened up a lot of new areas on which we are now working. And this is the new example that I worked with the group at University College London of Shogato Bose and myself, who was my ex-student earlier, and my other ex-student also there, and an experimenter from from the University of Southampton, Professor Henrik Wilbrich. The important point is that here we propose a linear harmonic oscillator system whose initial state is the most classical-like state, which is called the Schrodinger coherent state, which is the minimum uncertainty product state, non-spreading, peak following classical motion. So it is the most classical-like quantum state. Now with that state, with that state oscillating, so it is a pendulum kind of object, oscillating objects, and you measure which half the particle is in. So the measurements are dichotomic, either right half or left half. And then you study its temporal evolution, its oscillation, and measure the temporal correlations. You shine light on one half and see whether the particle is there. You measure repeatedly subsequently. So at consecutive instance, you measure the probability of finding the particle in this half or the other half. So consider a pendulum and you are watching in one half or in the other half, and measuring the probability of the particle being in right half and then again after a time in the left half. So this sort of temporal correlations are considered. And there was a novel ingredient we introduced which differed from other ways of using Leggettger. Here we consider two different observables at successive instants, and that led to, now this is some technical details I'm skipping, that how actually you should make measurement to ensure non-invasive measurability. You shine light on one half. So if you don't find it there, you know the particle must be there. So this is interpreted as the measurement of the outcome corresponding to the other half. And you retain only those outcomes where the probe has not interacted with the system. And those outcomes are used to test the temporal correlations and whether they violate the inequality, which is derived from realism and non-invasive. Now, in this sort of setup, you satisfy non-invasive measurability in the classical sense. Of course, the light is shown on only one half. So if the particle is found, you only take those outcomes. So the particle has not interacted with the probe. So it should not be affected. So it means that if you observe a pendulum by shining light on one half and you don't see it there, and in this way, if you make observations, then no, this is one details which I'm skipping about our particular scheme, how you do that. Then what is interesting that then you find violation of macrorealism in a mass independent way. And it becomes also independent of whatever be the angular frequency and its peak momentum. So that means it gives lot of flexibility of choosing the experimental parameters to minimize decoherence and other noises to see this effect. So this scheme has opened up the implementation with masses of the order of 10 to the power minus 15 kg. Or also there is a tantalizing possibility now that with LIGO, the gravitational wave detectors mirrors, they are of the order of 10 kg and they have been able to ground state cool it. That means it is quantum behavior of those mirrors have been established. And 10 to the power minus 14 kg mass means basically mass of a small, it's a small dust particle, a very fine grained dust particle mass. But there are now levitated nano objects have been made, levitated nano crystals. I do not go into the details, but it's a fascinating material. So there are experimenters now collaborating with us. I'm skipping all these details. This is just a glimpse of the result. So this sort of the violation, it is an inequality giving a bound of 0. So the violation is quite significant, predicted for any mass. So you see, for any mass in principle, you can get a violation of this order compared to 0, non-zero, the bound being 0. And then this has been called Schrodinger's pendulum experiment in, for example, the article in Scientific American that wrote about this work. So this is the summary. This is what I call the levitated nano objects of that mass. And there is, so I am skipping the experimental details, how the detection. And finally, to ending this talk, I must, since Professor Leggett will be speaking in the evening, he will be talking about, of course, the realism, this general point of view I already talked about. And when the report on our paper appeared in Physics World, they contacted him for his comments. And then from his comments, what has emerged is that the directions for further sophistication of this experiment, because you see because I talked about the non-invasive measurability being satisfied by shining light on one half of the year. Now, to experiment of testing such fundamental things, one should be careful enough that still, no matter how, because it is not possible fully to shine a light with a sharp drop in profile at the middle or whatever, so that no light affects the other half. So how much have you ensured that? So some control experiment has to be designed to measure whatever classical disturbance may have occurred in such experiments, which are called negative result measurements, because you take only the outcomes where the probe has not interacted with the mass, which is measured. But then how do you ensure that rest of everything is unchanged, not affected? So this actual experimental stuff has to be also ensured. That's why it is important to determine the amount of invasiveness of such measurements in practice. For that, a controlled experiment in this context is necessary. That we are trying to design now. Also, the magnitude of the effect I showed you there. Now, there will be, this is in the ideal condition, but there will be decoherence, there will be those other black body radiation effects, the vacuum has to be very high. Still, there will be some part of disturbance. So, it is important to enhance this macro quantum effect for this macro oscillator experiment. So, and finally, there are two remarks which I shall quote. One is that at the end of all this, Professor Leggett had remarked about this paper that these researchers are convinced that quantum mechanics is going to work, because the way we wrote this paper was testing quantumness. But paper said, how do you know quantum holds? So it is not testing quantumness, it is testing non-classicality. So testing quantumness indicates a bias that we believe that quantum mechanics should work. He would like to, he says, I am not so confident. So you may ask him more about this after today he gives talk, why he believes, why he has this. He will elaborate. This is his favorite topic, I'm sure. He will elaborate on that. And another remark I finally at the end of this measurement problem, Stephen Weinberg, this is a very, although he has not, yes, he has thought much about foundations, written also, but not that much. So towards the end of his life, before he passed away, he wrote a beautiful article in New York Review of Books on quantum measurement. The article is titled the Trouble with Quantum Mechanics, because this is the central problem of quantum measurement. I wish I could have spent more time. I hope Professor Leggett will speak more about it. So there Weinberg ended his article. So this is the way I prefer also to end my talk. He said that if one asks now to ask me about the future of quantum mechanics in light of these foundational problems, he says, I can only echo Viola in Shakespeare's Twelfth Night. Those who have read Shakespeare's Twelfth Night, Shakespeare's play. So there is the character Viola, who said, "O time, thou must disentangle this, not I." So I would also like to end it this way. Thanks. But I must say that many things have been unsaid, many things due to very shortage of time. So I just said this to provoke discussions, queries, and then there's much to be said and clarified. Hope you at least got some flavor.
Yeah, okay. The question maybe that you can.
Thank you, Professor Holm. I wanted to seek a small clarification regarding Bell's inequalities being viewed as giving up of locality plus realism. That would suggest that I'm okay if I give up one but not the other. Say like in non-local hidden variable theories, you give up locality but you retain realism. let's call that deterministic non-locality. We could probably try for the other thing where you give up realism but retain locality. I could call that indeterministic locality. Would it be right to say that in principle, Bell's inequalities could be violated for indeterministic local systems?
Now, this whole issue of what the Bell inequality violation means has been, particularly, I'm glad you made this question. This gives me the opportunity to talk. This is very important, so let me spend 5 or 10 minutes. Because recently, because I happen to be also part of this, there has been a debate involving Nicholas Gisa, who had raised this question fundamentally in 2012 in an article. He wrote an article in the Science called Non-Locality, How Does Nature Do It, and so on. And also recently came to the conference here. And about which he had some, also Professor Leggett has just recently written. So the whole issue is that the point that also my own, after studying this issue, is that if you look at the CHS inequality, the stochastic derivation, there is the input of realism there. Where is the input of realism there? Becomes difficult. The realism input is only in assumption of the reality of inputs and outputs, because it is a factorizable condition, closer on. And the factorizable condition is a statement of locality. So that made Gisa to argue in that. In fact, the title of the Gisa's paper will be provocative for you. It says, non-realism, soft option or hard reality, or something like that, hardcore. So if you take that CHS derivation coming from that non-factorizability condition, it is difficult to find any input of locality there, except where inputs and outputs are assumed to be definite, the input of realism. Inputs are assumed to be real, outputs are assumed to be real. Now, inputs definite reality, if you assume the free will of the experimenter, there are people who'd also now have challenged that assumption, whether you can derive condition. That is a separate. If you believe in the free will of the experimenter, then inputs are also real. It is fully under the control of the. Now, the output reality, there, Gisa admits there's a connection with the measurement problems, that within quantum formalism, the output has no. So, one way of viewing this way of could be that it is both. So, you have the option in that sense. But the option comes in this subtle way. No. So that's why measurement problem gets linked here with non-locality. This is not in the usual understanding, has not yet been properly emphasized. But then Gisa's own view, which was stated there also, is that no, I think ultimately the violation of Bell has to be interpreted as violation of locality. That is the non-locality is the fundamental thing. And that is where this, and then Leggett recently has an article in the journal, Probability. It is a beautiful article about the implication of, I have not talked about, when I stated hallmarks of classical worldview, I have omitted many aspects. The realism could be contextual. And also another very important aspect, which I hope very much, and I'm sure Professor Leggett will bring up, is the whole issue of counterfactual definiteness. Because the Bell inequality can be also derived by stating the realism, replacing realism by the assumption of counterfactual definiteness. So then what will you say about the meaning of the experiments violation of Bell? It has to be interpreted as violation of counterfactual definiteness. Leggett-Garg also can be done. So that's why Leggett now distinguishes between macroscopic counterfactual definiteness, which is applied in the context of Leggett-Garg, or Bell, which is microscopic. So what does violation of Bell and Leggett-Garg mean is still a very question. That is the question which needs to be explored. And this is, I think, 100 years of after quantum mechanics. To give rise to further new technologies also, this this will give this. I'm very glad you asked it, because this is should really. Here one has different viewpoints. I already mentioned. Right.
Professor Holm, there are several other questions. So
just to complete, and also I think it's far deeper. Why Jisa? I asked Jisa, why is so adamant in taking it to be as a violation of locality, ignoring that part? He said measurement problem is, of course, he fully appreciates measurement problem, agrees it is a fundamental problem. He all these things, but still he's fascinated by non-locality implication. And he says this the most important question is, how does, this is, I like his way of saying, how does nature organize its bookkeeping to fix the measurements which give rise to non-local correlations? So this question he considers to be the most. So this gives you a flavor that how means fascinating, intellectually fascinating his subject is, where these great minds can differ. And after all these years of so many people working, still the questions. And as was emphasized in the opening session, the importance of keeping openness of mind in all these debates. You see, we may have differences, but how to preserve this openness. And David Bohm, I did postdoctoral with David Bohm. And when I asked him to write on my thesis, what is his advice to me? He wrote, after all his interactions, he's worked with Oppenheimer as a PhD student. He has interacted with Einstein actively, hard Einstein board debate. He wrote, it is hard to, the most difficult thing is to keep an open mind free of prejudices. Thank you.
Yeah. So one question is that in quantum measurement, is it based on the assumption that measurement will always successful?
Oh, this is a separate issue. That means whether successful means whether it, you say, suppose I toss a coin,
right,
and the coin falls, and it falls neither head or tail. So it can fall in a slanting way in the mud. Okay. And then the measurement is not successful. So in this sense, here, so you have to here what I was saying, ideal measurement. Which are talking about ideal measurements.
Yeah. There is a question from this Ankur Haldar. His question is that, won't decoherence affect the quantumness of massive objects?
I have not touched upon it at all. This is why last I say, this is very important, decoherence. And also, in fact, in a real world, the wave function I wrote with system apparatus, it will be coupled to environment, many degrees of freedom. But, and it will of course affect the macros. That's why it is important, if you go and read our paper, the last part of the paper is totally devoted towards analyzing the conditions of decoherence in an actual experimental realization, how it would arise. So that study is important, and that's why one has to keep, I quoted some figures there. So what sort of vacuum will be required, what sort of low temperature will be required. So this experiment I proposed, our proposed experiment, which is being attempted at University of Southampton. And just to tell you also, so this experiment, since it requires very high vacuum and other stringent requirements to satisfy the requirement, a proposal has been made to run this experiment on the satellite. And so in this month itself, an European Space Agency satellite, a prototype is being mounted of this experiment in this month's European Space Agency to test. So it is a hard effort to do this kind of experiment, and the estimated time is about 4 to 5 years. This is it. But it is a very pertinent question, and we can discuss more how actually the decoherence is being attempted to minimize there. And that is why all the more important, as I indicated, to enhance the magnitude of these predicted effects. Whatever effects I predicted, the numbers I gave are for ideal conditions. Under decoherence, it will be affected. Means there will be the superposition will be destroyed. So you have to enhance the effect. And we are working on a powerful new technique for enhancing such quantum effects, such quantum mic. That will be the next exciting direction, that how best you can enhance the macro quantum effects. And these macro quantum effects, since I've got the chance to speak, I could not speak. People are now studying how this can have application in quantum sensing of gravity, minute gravity, quantum sensing of gravity or magnetic field. So this sort of quantum superpositions will have practical usefulness also for quantum sensing. So this is how technology, philosophy, conceptual, all these studies are getting intertwined.
Yeah. So this is last question. So if we are capable of showcasing the mass independent violation of macro realism, doesn't it then provide a contradiction of theory and practical experiments where we see objects to lose the properties of violation of macro realism with mass?
First of all these things, for example, quantum non-locality, or even to see them, you require special conditions. Like you will say that I think it is very misleading when people talk about, in fact, Schrödinger cat or the Einstein statement, is the moon there when nobody looks. For those kind of, for an actual cat, for an active, you'll never be able to show a macro quantum effect. But the point is, you can show this sort of effect under controlled laboratory conditions for special kind of systems. And for that, and that special kind of systems you are designing, which are way above the microscale. And more importantly, the other parameters are chosen such that, so that the collapse, the other kind of modifications of quantum mechanics that have been proposed. So those modifications give some concrete predictions at that scale, which can be tested for some scale of mass, some scale of distance, some scale of time, where there are some verifiable predictions of modifications of quantum mechanics proposed, if those can be tested. This is the main goal of this experimentally oriented studies of foundational issues of quantum mechanics. I may call this line of study this, by meaning that all those foundational issues or interpretations, models, how to make them empirically relevant, testable. For that, you need to stretch the limits of technology and experiment. So this is how the progress is made. And this is the way forward, I think, for the next few decades after this 100 years of quantum mechanics.
So we wrap up the question answer session here, and then we'll get more time during this lunch and lunch break. So let us thank once again to Professor Hom